Hello everyone, welcome to the Isaac Sim 2020 Deep Dive. My name is Hai-Lok Lu. I'll be covering the first half of the talk. My colleague Hamad will cover the second half. Let's start. This is the agenda of the talk. We'll go over the Isaac Sim feature overview. What can Isaac Sim do? Where you can get it, all its features currently. And then we're going to talk about the 2020 roadmap, where we are and where we are going, so that hopefully you have a better idea of how Isaac Sim might be able to help you in the future as well. How to download and run Isaac Sim. Isaac Sim Docker container can be run on AWS, on the cloud, or locally on your Ubuntu 18. And then we can stream the Docker container images to the Omniverse Kit remote client for viewing and interacting. And we can connect the Visual Studio Code for remote code development. Hamad will cover the code deep dive.
In terms of features, Isaac Sim is our NVIDIA's open robotics simulation platform. Developers should be able to download and try it out. It has a full editor, as you can see on the right-hand side, with both Python and C++ APIs, and they can talk to each other as well.
Isaac Sim features ray tracing graphics with the ability to scale to multiple GPUs and physically based materials, MDL. This is the key for us to be able to achieve realistic looks. And I think this is going to have, the perception stack as well as you train your robots, to perceive the world. It also has PhysX 5.0 with robust and performant articulation. So each robot can be an articulation, a collection of joints. We have GPUs, physics support. It also features the Riemannian motion policies library, or RMP, which enables or provides very smooth and lifelike movements for the robot. We will show this later. And of course, Isaac Sim is containerized for running on the cloud, on AWS, or locally in your Ubuntu 18 with streaming and interacting. I think this is quite important. Robotics researchers working from home, who don't have access to a powerful machine can use, Isaac Sim on the cloud and stream down and continue to do their work from home. We'll talk about the UIDF importer, how you can bring your own robot into Isaac Sim, and more features to come. In terms of roadmap in 2020, about a month ago, we shipped the Leonardo manipulation application. It was built based on Isaac Sim. The Leonardo applications has the ability to perform this specific stacking blocks task. It features the Riemannian motion policies, or RMPs, so the robots are able to move in a very smooth and lifelike manner and avoid dynamic obstacles. We'll show this more in later slides. And of course, all the features that I talked about, running on the cloud or locally, ray tracing and, PhysX 5.0 articulations. So in May 2020, we will ship the Isaac Sim 2020.1 with both navigations and manipulations. As you can see, some of the robots in here. We will support the Isaac SDK, our Isaac SDK, and ROS. Developers should be able to use, both Isaac SDK messages and ROS messages to communicate with Isaac Sim. In terms of sensors, it will have RGB-D camera, RGB and depth, LiDAR, IMU, segmentations, and bounding boxes. We also have a model pipeline that allows developers to import ShapeNet objects, bring in more objects into your environment, and of course, cloud and workstation. A bit further out in Q3, we will try to combine the mobile arm, many robots combined together, like this Franka arm combined with our Carter mobile base and ROS2 support for Q3. So where can we download Isaac Sim? If you go to this website, developer.nvidia.com/isaacsim, you can see the download button on the bottom right-hand corner. You will need two accounts. The first one is the NGC account to download the Isaac Sim Docker container. So NGC is our GPU optimized software hub that hosts all the containers for running on the cloud. It features a lot of GPU optimized softwares. The second account that you need is the usual NVIDIA developer account to download, the user guide, the streaming client, which runs both on Windows and Linux and other cloud configuration files. So two accounts. One is NGC account to download the Isaac Sim container, and the other one is the developer account to download the streaming client and other things. I'll run through all the steps in the later slides. So how we run Isaac Sim. So basically, the Isaac Sim container can be run on the AWS instance or your local Ubuntu 18. And the container can be downloaded from NGC, NVIDIA NGC. Once we run the container, we can stream the images to the Omniverse remote client, which runs both on Linux and Windows. So the left-hand side, the Isaac Sim container needs to be run on Ubuntu and on a Ubuntu instance, but the remote client can be run both on Linux and Windows. And then we can connect the Visual Studio Code to the container instance for remote editing and code development. For the launching the AWS instance, we can use the manual step or using Terraform. I will run through all of these 4 steps in the next videos. Be sure that all these steps are captured in our user guide. So, if things are a bit fast, you can always refer back to the user guide. All right, let's see how we can launch the AWS instance using the manual step first. So this is the AWS console. You can click the launch button. Here you need to select an AMI which specifies which graphics driver that the Isaac Sim needs. You can search for the AMI in the community AMIs, and then using that specific keyword. And then you need to select a GPU instance. Let's say in this case 4x large. Click next. These are the default settings that we can leave as is for now. We need to increase the storage from 8 to 32 to be able to extract the container image. Enable certain ports so that we are able to HHH in and for the Visual Studio Code and the streaming client later. And now we'll click launch. It will ask for an existing key, or you could create a new key. I'll create a new key for now and give it a name. Then you can click download the key pair. It will download down to your browser download folder, and we can use this to HH in later. Okay, so now it is launched. As you can see, this is the instance that we just launched. This is the public IP address that you can use later. Okay, so now we launched the AWS instance. Let's see how we can SSH in and download the Docker container from NGC. Another way to launch the AWS is using Terraform. So the previous video that I showed, we use step-by-steps or the manual steps. With Terraform, you can run 3 commands, Terraform init, plant, and apply. It will take care of launching the instance for you, download the NGC container, and launch Isaac Sim. It is more convenient, but you need to refresh to see where you are in all of those 3 steps. The manual step, you know exactly where you are, but Terraform is another option to launch an AWS instance. Okay. As I said, all the steps are here in the user guide. It contains a lot of good information, like the steps that I described. Also, the code deep dive that Hamad will talk about. All right, let's back and see how we can SSH in. You select an instance and click that connect button up there. First, we need to chmod 400, the key that we just downloaded. And then we can SSH in -i and specify that key with, the instance name that we just launched. It should say succeed now. And we can run NVIDIA SMI to verify that the card we are running is the Tesla T4. And now we need to log in to NGC by running the sudo docker login. You ask for username, that is the username. And then the password, you can get it from the NGC website when you register, like here. Go to setup, get an API key, and then generate an API key. It will give you the password, and you paste the password in here. It should say login succeed now. Right. Now we can download the PhysX container Docker image by running, sudo docker run and specify the link. Again, all the steps are captured in the user guide. Once it's finished downloading, it will ask you to accept the EULA. Just run the same command again with the accept EULA. And now the PhysX is running. Okay, so now we have the PhysX running on the AWS instance. The next step is connecting the Omniverse remote client to see what is going on. You launch the Visual Studio, the Omniverse remote client, specify the IP address with the resolution. This is the kit, the Omniverse PhysX UI that you see. If you click the create scenario, it will import in all the robots in your scene. In this case, Franka and other objects. The left-hand side is the normal transform widgets. The right-hand side are all the objects in the scene. Now it's finished compiling the materials. If you click play, the robot will start simulating. And when you click perform task, it will start stacking the cubes. So the orange arms are other possible trajectories to reach the same target. Again, the RMPs allows the robots to avoid dynamic obstacles. As you can see, you can safely interrupt the robot. I think this is quite important to test, your algorithms in a safe manner. Okay, now that we ran PhysX and see what it's doing, let's see how we can connect the Visual Studio Code to do some code editing. As you can see, all of these tables and the Franka, we have this exact same setup in real life as well. This is Chien, our colleague, interacting with the real robot. This is Dieter Fox leading the robotics research lab in Seattle. Amazing work they've been doing. As you can see, the real robots and the robots in PhysX are using the same algorithm, so they're behaving exactly the same. This is how we are able to use PhysX to test. Okay, let's see how we use Visual Studio Code. So this is Visual Studio Code. To attach it into the AWS instance that we launch, we'll need to specify the SSH config file. Host, you can, that's the name of the config file. Host name, you can use the public IP address. And then the identity file, point to your security key or PAM key that we downloaded. And of course, users, you want to save this file and then try to connect to a host with that Leonardo host name. And now it's to say succeeds. So once we're in, we can open the source file. So they pointed to the source file in this case with this path. Again, all of these steps are documented in the user guide. So this is the Leonardo preview.python. So all this Python code, all the create scenario, perform tests. So this is where the code is, as you can see. Now, let's say we want to make some code changes. We can do that. Let's say we want to add another button like this. The important thing here is you can make code changes on the Python side without having to recompile Isaac Sim at all. So this is very fast for development. Let's say we create an awesome scenario button, and immediately the button appears over here. So that is the end of my portion. Now let's move on to Hamad. Thank you.
Right. Thanks, Locke. So in this next part of the talk, I'm going to go into more details about how the code is structured and how you can, in general, use Omniverse Isaac Sim for simulation-related tasks. So to start, I'm going to talk about how the front end for Omniverse Isaac Sim, which we call Omniverse Kit, is laid out. So this window has a lot of stuff going on in it, but the most important stuff I've highlighted in the colored boxes. At the top, you have a menu which provides you the physics authoring tools, and these are important because this is where you would do things like create rigid bodies, create joints between rigid bodies, and set up your physics settings. On the left side, you have your widgets and simulation control, kind of the general things that you'd expect in such an editor that would allow you to move objects around and then start and stop simulation. In the center, you have your viewport, which is where all the graphics are being ray traced, and you have your lights and other objects. On the bottom is where the Leonardo preview application that came with the release is running. And that's where you can, as Locke showed earlier, create your scenario, perform your task, and also live edit. If you want to change the UI, you'll see the changes down there. On the right side is probably the most important part, and that is on top showing the stage window. And that is where you see a tree-like hierarchy of all the objects in the scene. And how they're organized and the parent-child structure. Now, if you were to click on an object, in this case, I've clicked on one of the joints, you'll see the details panel will automatically populate with all the different attributes and properties that that joint has. And you can change them dynamically. So if you wanted to increase the joint stiffness and stuff like that. Now, I want to go into a little more detail about how does the editor basically work alongside PhysX and USD, which is the Universal Scene Description format. So USD is a format that came out of Disney Pixar, and it basically provides you a single representation for many different kinds of data, geometry, materials, physics. You can have your own custom metadata inside of there. And how we organize things is that we have a stage. And a stage is a collection of USD primitives, which can be of any of the aforementioned types. And these prims can be of like a X form, which is a transform that you can rotate and move, a mesh, which would hold some sort of geometry, joints, lights, cameras, things like that. And depending on the type of primitive that you can have different attributes on that. If you can imagine, a light would have additional parameters dealing with brightness and the type of light it is, while a joint would have things like joint stiffness and so on. Now, let's say you have a primitive, like a mesh being something with geometry that you can transform. If you wanted to add physics to this, you could apply different schemas that would provide different additional attributes that are then automatically read in by the physics plugin and then simulated. So in this case, you could apply the physics and mass APIs, and then the object would fall due to gravity. If you wanted to apply a collision mesh to the existing mesh that you had, you could add the collision API and then enable something like convex decomposition, and that would allow that object to fall and hit the ground and interact with other objects. Now, all these attributes, it's important to note that they can be modified from inside of the editor. You can also use the USD Python API, which comes with USD. Or if you were to save the USD file out to disk as a USDA file, you could modify that directly in ASCII. I want to highlight this link at the bottom. That link is a really good resource for finding out more information about USD in general. We also have links to the Pixar documentation and their tutorials, and we have our own tutorials there as well. So what is kind of like, so we have an empty editor now. How do we get a robot into it? Well, we have a few ways of doing that. The first is via URDF files. URDF files are pretty common in the robotics field, especially if you're using ROS. And we have a one-way import built into the editor that when you go file open, you can file open a URDF and it will automatically perform a one-way conversion, which will convert all the meshes and as much of the valid URDF properties that it can into the physics side of things. Now, there are a couple of caveats with this. The first is that your URDF file is going to be XML, and that XML must be as standard as possible. If you have mistakes, random, non-terminated items, the import will fail, but you can look at the console when you do the import, and it should tell you some helpful information about where the import failed. From the mesh import side, OBJ files are the best in terms of support, but depending on how you exported your DAE files, those will sometimes work. We recommend that you use OBJ files, though. The next way to create a robot is, let's imagine that you had imported visual meshes for your robotic arm. Now, in this preview release, we're somewhat limited in how we can import meshes, but in the next release, you will be able to import directly from the editor FBX files, OBJ files, and a couple other formats. Now, once you have your visual meshes imported, you can, using the physics menu, create joints between the visual meshes, assign them to rigid bodies, apply mass. There is a special PhysX properties window they can use to dial in some of the custom physics properties. And it provides you a richer interface than the details panel provides. And then finally, let's say you wanted to write a robot from scratch. Well, what you could do is you could start off in the editor by making, let's say, a rigid body and a joint, and then save that to a USDA, A being for ASCII, meaning it's humanly readable. And then inside the USD file, you could copy paste the joint and rigid body and then create your own structure and then set all the local transforms and so on. I did mention earlier that USD has a Python API, and all of these things, anything that you can do in the editor is also accessible through Python. So if you wanted to have a parametric robot generator that would take different rigid bodies and joints and assign them in different ways, you could do that. And it's actually pretty straightforward. The Python API is really rich on the USD side. Next, I'm going to show you a video of what it looks like when importing a URDF model. So hopefully this plays. Okay, there we go. So in the beginning, I imported the URDF file and it immediately converted all the meshes. I then add a light just so that you can kind of see the robot move better. And once I enable simulation, I can click on a joint and immediately start dragging around its joint drives. Now, when you import a robot by default, all the drives will be set to position drives with some generic stiffness, max force, and damping values set. Those should be tuned depending on the robot that you have. Here, the defaults are just kind of enough to get you going so that you can see that the robot is moving. And then next, I wanted to show, again, the Leonardo preview. So in the next set of slides, what I'm going to be talking about is kind of how this application was built. Now that we have a robot imported, how do we make it move like this? How do we make it avoid obstacles? and what those ghosts mean. So whenever you see one of those orange robots come out, what that's actually showing you is a different motion plan given a different default configuration. So imagine if the robot had its elbow out to one side, how would it try to reach the same pose? Now, in this task, the most natural way to perform stacking is via the solid robot pose, basically straight up and straight down. But we do show that it is possible to simulate alternate trajectories live. And if you wanted to, you could decide what the best way to reach something is. Okay, so let's look at a quick diagram of how this was all set up. Okay, there we go. So this diagram is trying to show a high-level overview of how the Omniverse Isaac Sim framework, which includes Omniverse Kit, which is the editor, a bunch of extensions for ray tracing and things like that, tie into the rest of the Leonardo preview application. So on top of Omniverse Isaac Sim, we have a few C++ libraries, one being the PhysX plugin, which provides support for physics. We have dynamic control and motion planning, which I'll go into next. And then on top of these C++ libraries, we expose Python APIs for everything, such that you can build on higher level applications. So on top of this, we would build our simulated Franka, which is supposed to replicate what you'd have in the real world, as well as creating the state machine and high-level task planning. So what is the dynamic control API? So we found that while the physics API is very rich, in some cases it is a little bit too verbose when you want to do robotics applications. So we still provide the full PhysX API to the user, but we also provide this slightly higher level API called dynamic control. The main use case, at least why I find it interesting and useful, is that whenever you press play and stop instead of the editor, the PhysX state is destroyed and recreated. And that is so that all the physics pointers can be cleared up, and if you make any changes on the USD side, they can be re-replicated back into PhysX. Now, the downside is that if you did have a PhysX pointer, it would disappear as soon as you press stop. And if you try to do anything with it, your program would crash. So dynamic control provides an API through USD where you can get a opaque dynamic control handle to the PhysX object through a USD path. And whenever the PhysX pointer underlying it changes, it is automatically updated, and things will continue to work without any trouble. Now, at the bottom here of the slide, I'm providing a pretty simple code sample. And the one thing I wanted to point out is that that path that I have for the get articulation call is a path that you'd find in the stage window. So generally, everything is organized under a root X-form prim called world, which has usually a 0 transform. And underneath that, we have a robot Franka, and then the specific robot Panda. So what this code sample is doing is it's showing how you can get the articulation from that USD path. And you have to wake it up because the physics simulation will try to put objects to sleep that are not moving. So in case the robot's not moving, you need to wake it up so that when you set the position target for each degree of freedom, the robot will move. So here's a quick video basically showing what that looks like. So inside of the Omniverse Kit editor, we have a really useful scripting window. And in there, you can basically write Python live and run it. And what I find this most useful for is before designing a plugin or extension inside of Isaac Sim, I want to prototype the physics, make sure everything is working. If I'm importing a new robot, I can easily play with it inside of the editor by just writing Python code. And there you saw me running the same script over and over again to make the joints randomly move. All right, so we imported a robot into the simulator. We now have a way to control its joints using physics. Well, the next thing is generating a motion plan so that you can give high-level commands. Now here we leverage something called Riemannian motion policies, or RMPs for short. And I'm not going to go into details, but basically the idea is that your robot has a task space in terms of joints. You have the 7 joints plus the 2 for the fingers. But from the robotics side, you generally want to control the robot from its end effector. So you want to move the end effector forward, backwards, left, right, up, down. RMPs provide you a way to optimally compute the joint angles given a more natural kind of world space pose for the end effector. And if there are obstacles in the path of that robot, it will automatically avoid them for you. Now, the API that we provide is pretty straightforward. If you wanted to import a brand new robot, you would need to provide a new YAML config. We have one in there for the Franka robot, but let's say you had a UR10, you could modify the YAML config to add or remove the joints needed for your new robot, and then tune the parameters there such that your robot moved optimally. For the next release, we do plan on providing a little bit more documentation for this. Right now, it's a little bit hard to change the robot, but it is possible. Another thing in the API is that you can specify the end effector pose in the robot coordinate frame, which is the coordinate frame corresponding to the base of the robot. You can add and remove obstacles, and these obstacles are defined using primitive shapes such as spheres, cubes, cylinders. And once you have your obstacles, you can update them every single frame via ground truth data from PhysX. So that is where you would want to, for example, all the cubes and blocks that you saw in the Leonardo stacking scene, every single one of them is updated per frame from the PhysX data. And at the bottom, I have a reference for if anyone's interested, if they want to read the paper about RMP. It is out of our group, out of our Seattle robotics lab, led by Professor Dieter Fox. And here's a quick video showing what the obstacle avoidance looks like. This is one of the 3 samples that we provide as part of the Leonardo preview. This would be the obstacle avoidance sample. And here we have 2 Rubik's Cubes, which are just moving in a sinusoidal pattern where the robot is trying to maintain a fixed pose, and it will automatically avoid the cubes and try to reach that fixed pose as best as it can. We have 3 examples total as part of this release. The first one being the ghost robot fully stacking scene. We have another one that stacks 2 blocks, and then the final one, it avoids obstacles. And the idea here was to provide 1 full example, and then 2 simpler examples that could be ripped apart, put back together to build more complex scenarios. So next, I'm going to talk about the Franka interface itself. So we have the robot being simulated, we have the way to interact with it, we can provide high-level motion plans, but now we want to somehow have a way to interface with our simulated robot, exactly like we would for the physical robot. So here in Franka.py, we have a Franka class which initializes the motion planning framework, loads all the config files, sets everything up. Inside of this class, we have an end effector, and this naturally is what you would send your end effector target commands. And we have a function called goLocal, which means you want to set the local pose, set the pose of the end effector in the local reference frame of the robot base. This then sends the target request to the motion planning extension, which then runs the RMP code, and that will automatically, every single frame, update the robot and try to move to that target. We have a gripper class, which allows you to open and close the gripper fingers. The gripper is separate from the end effector because, as you can imagine, you can have a fixed robot arm, but then attach different end effectors to it. So this would be the point, let's say, if you wanted to attach something like a suction cup gripper, you can modify the gripper class and interface with that. And then finally, we have a status class. And the main use of this is that inside of your code, you want to know what the status of the RMP is and if it's reached its target. So every single frame, it updates where it currently is and where it is being told to go. And if you wanted to query whether it reached its target or if it's within a threshold, you can check the status and then do that distance computation and so on. Okay, so we now have a simulated robot. Well, how do we generate kind of tasks in terms of super high level, I want the robot to do X, Y, Z? We provide a simple but powerful state machine in statemachine.py, which is based around a hierarchical state. And this hierarchical state, it has a couple of basic functions. Oh, and I also apologize for the numbering this slide. It kind of got weird. I don't know why they're all 1. But in this hierarchical state machine, you have a function that is called whenever you enter a state, exit a state. Every single frame as you step through that state, there's a transition function where you can check to see if you're ready to move on to the next state. And then as part of this, you can provide additional hierarchical states. So init state is the state that you start at, active state is the current active state, and the next state will be the next hierarchical state that you want to transition into once the transition condition is met. Now, all of these states are defined in behavior states.py, and that, for example, is where we have a pick block state machine, which does a basic simple, it moves above the block, goes down and picks it. We have a place block, which then places the block and lets go. We can build higher level tasks called, for example, pick and place machine will do both the pick and place operations. And then finally, we can build the full state machine, which is what we use for the ghost robot scenario in stack blocks economical, where it does the it looks at a block before going down and reaching for it. The ghosts come out and show kind of potential motion plans that the robot could have done, and so on. The example that does a simple stack, which is basically it picks up one block and puts on top of the other, is a really good way to learn how to build your own state machine. And it provides a pretty simple example that is easy to read, and you could make that more interesting by adding more blocks or stacking in a different way. So going back, to put in context, I just talked about how the Leonardo preview application was built. So the goal of all of this is that we want to provide Python APIs for everything, where you can rip out whatever piece that you wanted. So for example, let's say you had your own motion planning code. You could integrate that via Python, replace our entire motion planning stack, and have your own controller. If you want to interact with PhysX directly, you could get rid of the dynamic control side and have the low-level PhysX access. If you wanted to change the robot, you could get rid of the simulated Franka and introduce your own robot class that would leverage everything else, motion plans, dynamic control, or any subset. And then on top of that, introduce your own state machine, your own high-level task planning that it would interact with the robot. So the goal of this preview is to kind of show where we're going with Omniverse Isaac Sim and trying to provide a Python-centric interface that also gives you access to C++, the rendering, and things like that, so that you can build interesting robotics applications and do research on top of that. So to end with, I'm going to talk about what's in the next release. So the focus of this next release, apart from improving support for navigation and more manipulators, is that we want to get into synthetic data generation, which is very important when you want to train your robots, your classifiers, pose detection networks, things like that. So to this end, we're going to have support for ground truth sensor simulation, starting off with RGB depth cameras. We'll have LiDAR simulation, the ability to get ground truth bounding boxes, as well as segmentation both for the classes and instances. Now, synthetic data generation is kind of useless unless you have a good way to randomize your scene. So we will provide a domain randomization toolbox, which will allow you to leverage a lot of different functionality, which I'll show in the next slide in a video. But it allows you to randomize many different aspects of the scene, like lighting, camera position, object position, textures, materials. And that combined with the ground truth sensor simulation will allow you to parametrically generate your environments. You could do training kind of in a randomized fashion, look at edge cases, and things like that. We will also provide communication layer support for ROS1 to start with, and as well as the Isaac SDK. The Isaac SDK will be the primary the primary SDK used for the navigation samples. But if you had your own navigation stack running in ROS, there should be no issues running that with Sim. We will also provide more assets and environments. In the original Isaac Sim release with UE4, we had a lot of different environments. We had an office, a hospital, a warehouse, and we were going to start pulling some of those into Omniverse Isaac Sim, starting off probably with the warehouse. And the idea there being that we'll provide a lot of the building blocks that you would want in a warehouse, like shelves and boxes and lights and so on. And you could reorganize those and generate an infinite number of warehouses by parametrically moving those objects around, randomizing them, things like that. We will be supporting more robots. In that image, we show the Carter robot, which is our kind of navigation base that we use for navigation testing, as well as the UR10 robot. And we'll also document better, I guess, how you can create robots from scratch and things like that. A lot of the tooling that was in the preview release has been improved upon by the PhysX team a lot, and now it is much more intuitive to build robots. So to end, I have two videos. The first one showing a contrived domain randomization example. So here you have a scene with the blocks are being moved on the table. We have light being moved around. The color of the ground and the block on the right are randomized. And the background textures are being randomized as well. Now, obviously, in an actual scenario, there'd be a lot more happening, but we just kind of wanted to show some of the basic features that you would get with this. And then finally, the last video, it shows a navigation sample. So basically in the Omniverse PhysX sim, we have this Carter robot driving around our little block world, and we have the camera data being sent to the SDK, where it then uses LiDAR and the camera to localize and then navigate between different waypoints. And with that, we will transition to the Q&A section.
Thank you, Hamad. I'll try to answer some of the questions that you guys have posted. I think the most common question is, what is the minimum hardware can it run on, certain card? So because PhysX Sim is featuring ray tracing graphics, so if you run locally on your Ubuntu 18, it is recommended that you use the RTX 2070. That will ensure, certain optimal performance. Anything above it, that should be good. 2070, because it might be able to run on older cards too, but we can't guarantee the performance. And of course, you can also run on AWS, which has the Tesla T4 cards. And when you run with AWS, of course, you need to pay for, the AWS service. But PhysX Sim container can be run locally on your Ubuntu machine. Another questions, the people ask is what kind of robots can be simulated. So as Hamad said, if you have a URDF file, you can try to import in. PhysX Sim will try to parse that and then import the robots for you. Of course, URDF might come with, like certain values might not be correct or are missing. We'll try our best to parse that, but URDF is one way. Another way, as Hamad said, you can try to set up your robot manually in the editor, importing your objects and set up the joins yourself as well.
So there were two questions I want to quickly answer. One is I didn't provide too much explanation for what URDF stood for. So that stands for the Universal Robotics Description Format. URDF files are generally provided sometimes by the manufacturers or by researchers. So, for example, for the Franka Panda arm, you can go to, there's a GitHub repository that provides you the URDF that you could load into ROS, into RViz, and that same URDF is what we load into the simulator. The UR10 robot, that is a robot from Universal Robotics. They have several different models. There's a UR3, UR5, UR10, and we'll probably support at least the UR10, but that will probably easily transition into the UR5 and the UR3 as well. There's a question about when the ROS2 interface will be available. Locke covered that in the beginning, so that is going to be our release following the one in May. We plan on adding ROS2 support. For now, we're supporting ROS1 because a lot of the researchers in the Seattle Robotics group use ROS1. So naturally, we have a customer internally that we can work with to make sure that our simulator works for researchers before we release that to the public.
We have one question about whether it support simulating the suction cup grippers. Yes, we can use a PhysX fixed joint to simulate the suction cup with open and close as well. There are other physics features that you can use to simulate different physics behaviors or effects, like applying forces. There's some wind and other physics features as well. Another question is, will it have the sim to real features to transfer to the real robot? So as Hamad said, we have domain randomizations, which helps your algorithms to be much more robust by randomizing, the looks, the physics properties as well, so that when you transfer to the real robot reality, it's just another randomizations from the algorithm point of view. Together with the realistic graphics, ray tracing graphics, I think that will have the perception stack as well. When your robot see very realistic camera images, just like real life, and together with the other exposed PhysX parameters that you can randomize, you can tune to achieve this sim to real.
So there was a question kind of related about how realistic is the grasping and manipulation physics in this release. So from experience, I can tell you that the physics is very realistic, but oftentimes the problem is that it is difficult to get the actual physics parameters. So you can have a robot arm, but unless you have the like a realistic mass, a realistic moment of inertia specified, the actual joint stiffnesses, the results that you get won't be physically accurate. So it's kind of the more physically accurate the parameters you give to the physics simulation, the more accurate your physics will end up being. There was also a question on what is the difference between Gazebo Ross and Isaac Sim. And probably the two main things would be that in Omniverse Isaac Sim, we're trying to leverage our ray tracing technology at NVIDIA to get photorealistic sensor images and sensor generation, especially for things like LiDAR, RGB cameras. We can do ray tracing, which would give us much more photorealistic images. And the second thing would be that because we have a support for PhysX 5.0, the simulation of robotic manipulators, especially when you're dealing with large mass ratios and a lot of different arms and different objects, is going to be more robust and accurate than other simulators that are out there, depending on your application, obviously. There's never one solution for everything, but we're trying to provide one that works the best in terms of performance and scalability.
I think we can take one more last question.
I guess there's a quick one. How many degrees of freedom are needed for the robot arm? That is entirely dependent on the robot. You can have anywhere from 1 to 10, 20. There's no minimum limit on that at all.